Hi all. Today we are looking at exponential functions and their graphs. Today we'll look at what is an exponential function and what are the basic linear transformations that can be applied to exponential functions. So an exponential function is one defined where a function is equals to some number raised to a power. In previous we would have the power being fixed, x squared plus 2x plus 8, for instance. You would have the power being fixed. But now what we have is that the base being a fixed number, while the exponent being the number that is changing. So first things first, we'll try to figure out how this works in terms of a exponential function, and also what we expect to see and understand from our exponential functions, i.e. what are their properties. So first things first, let's see if we can graph this function. Let's say I have f of x is equals to 2 to the x power. Can I graph this function? Well, alright, I think I can. So table of values, x comma y. And I'm going to have quite a few x values right here, so we can hopefully get a fuller picture of what the graph will look like. Okay, let's work these out one at a time. So starting right here with 3, f of 3 is simply 2 to the third power, which is 2 times 2 times 2. Exponential function is based upon using the base in multiple multiplications. And so that's 8, I believe. 2 squared is 4. 2 to the first power, and that's one of the rules that you need to learn about exponentials, but any number raised to the first power is itself. We often simply just don't write the exponent down. And so 2 to the first power right there is equals to 2. And then 2 to the 0 power, any number to the 0 power is 1. That comes from the fact, let's say I have 2 to the 5th divided by 2 to the 5th. When I am dividing, I subtract powers, so I keep the base and I subtract the powers, and that gives me 2 to the 0 power. Well, any number divided by itself is 1, so 2 to the 0 must be 1. In fact, any number. My goodness, that does not look like the word number. So let's just fix that right there. There we go. Any number raised to the 0 power is equal to 0, is 1. 2 to the 0 is 1, 5 to the 0 is 1, 200 to the 0 is 1, and so forth and so on. Oh, one thing I did mention, for exponential functions, the base must be greater than 0. We will not be having any negative bases right here, but also the base cannot equal 1. If the base equals 1, it breaks down to simply always being 1. And so we don't allow for the base to be 1 either. Alright, so you won't see any negative bases and you won't see a base of 1. So anyways, any number to the 0 power is 1. And so then that takes us to 2 to the negative 1. Now, for some reason, a lot of people, when they see a negative power, they default to multiplication. They say, well, this must be negative 2 because of the minus sign right here. Well, let's go back right here. In this example right here, did I go 2 times 3 is 6? Is that how I got the answer? No. So the negative power right here does not indicate multiplication. A negative power indicates a reciprocal. This is a fact that you must learn. And so this actually is the reciprocal of 2, or is 1/2, raised to the 1 power, which is just 1/2. So this right here is 1/2. The next one, 2 to the negative 2. Again, you do the power first. Reciprocal of 2 is 1 over 2, and that is being squared. 1/2 times 1/2 is 1/4. And so this right here is 1/4. And then 2 to the negative 3. That again, the negative sign right here means a reciprocal. It's not multiplication. It means flip the base. That's another way of thinking about it. And that's a 3. And so that's 1/2 times 1/2 times 1/2. That is 1/8. There we go. A defining rule about exponential functions is that the base is the change that you see. What is the base of this function right here? The base of this function is 2. Well, what's 1/8 multiplied by 2? 1/4. What's 1/4 multiplied by 2? 1/2. What's 1/2 times 2? 1. It's 1 times 2. 2. 4. 8. In fact, the next number is going to be 16. The next number is going to be 32, and so forth and so forth. Each time I'm multiplying by 2, that number comes from the base. So if the base was 3, each time I'll be multiplying by 3. If the base was 15, each time I'll be multiplying by 15. And so what we see for this function right here is that it is growing. Think about it. If I keep multiplying by 2, I double my size each time, right? And so attack of the viruses, viruses, they multiply. And so what happens right here is we're multiplying each time, and that's how we're getting the growth out of our function. And so that allows us to graph that function very nicely and very neatly. And so now this is going to be a little bit challenging. So let me see if I can get this done. -1, -2, -3, 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 4. And so I'm plotting points. Let's start in the middle. In the middle, I have a point at 0, 1. Then I have a point at 1, 2. And then I have a point at 2, 4. And then I have a point at 3, 8. Then I have a point at 4, 16. And then I have a point at 5, 32. Well, yeah, I can't get to 32. At -1, it is a half. At -2 is a half of a half, which is a quarter. At -3 is a half of a quarter, which is an eighth. And then 1/16, and then 1/32. And so you graph right here that starts real low. Basically, it starts out flat, and then it starts to grow and grow and grow and grow. We call this right here exponential growth, what you see in this picture. Should always give the function a name, so f of x equals 1/2 equals 2 raised to the x power, like so. Your properties here, the things that you notice about these graphs that will always be true, is that first that the domain will be all real numbers. The graph extends down to infinity and extends out to positive infinity. Another way of saying this is that I can plug in any number into an exponential function and get an answer. Second, the range. Exponential functions have this strange feature is that they never actually become negative. Think about it. If I keep dividing by 2, right? Because I'm multiplying by 2 to go in this direction. So to go in this direction, I need to divide by 2. If I keep dividing by 2, will I ever get a negative number? No. 4 divided by 2 is 2. 2 divided by 2 is 1. Both numbers are always positive. And so because of that, this thing right here will never be negative. Similarly, if I keep cutting stuff in half, I never actually get an answer of 0. And so the graph will always float above the x-axis. And because of that floating, the range is from 0 to infinity with a parenthesis on the infinity. The y-intercept is 0, 1. Any number to the 0 power is equals to 1. This graph is increasing. And that's because I keep multiplying by 2 as I go from left to right. And last but not least, this graph has a horizontal asymptote. Of y is equals to 0. And that is because, that's this line right here, the x-axis. And that is because the graph floats above that x-axis. And so therefore, horizontal line is the line that the graph approaches but never reaches. And so therefore, that is my horizontal asymptote right there. Alright, so those are our properties: domain, range, y-intercept, increasing or decreasing, and horizontal asymptote. Those are 5 properties. Interestingly enough, if I make a small change to the rational function, what changes will I see? So let's say that instead of graphing this function right here, I graph the function y is equals to 3 to the x. What I will notice is that 3 to the x still goes to 0 right here. When I plug in 1, the answer is going to be 3, and then plug in 2, the answer is going to be 9. So the graph is going to go higher, faster. Interestingly enough, when I plug in 1, I'm going to get an answer of 1/3, which is going to be below 1 right here. And so it's also going to get lower faster. But the interesting thing for the graph right here, 3 to the x power, all of these things are still the same. The domain is still all real numbers. The range is still 0 to infinity. The y-intercept is still at 0, 1, still increasing. And the horizontal asymptote is still y equals 0. So these properties hold. It could have been a 4 to the x, 5 to the x, 700 to the x. What we simply say is that the base must be greater than 1. That's all we're requiring. If the base is greater than 1, means I'm multiplying by a number that's larger than 1, and if I do, then I grow. If I have 5 chickens and I quadruple them, I get 20 chickens. I'm growing at a rate of a factor of 4. So, can I get these functions to shrink? Can I get these functions to get smaller? And the answer is yes. If I choose a base that is a proper fraction, my graph will actually not grow anymore. Table of values, x and y, -3, -2, -1, 0, 1, 2, and 3. Of course, I got to plug those numbers in. So 1/2 raised to the 3rd power is 1/2 times 1/2 times 1/2, which is 1/8. So 1/8 down here. 1/2 raised to the 4th power, it will be on the 4th squared. It will be the 1/4 power. And 1/2 to the 1 is 1/2. 1/2 to the 0 is 1. 1/2 to the -1. Again, the negative power does not mean multiplication. It means take a reciprocal. Well, what's the reciprocal of 1/2? It's 2. And so this is going to be 2. 1/2 to the -2 is equals to 2 to the 2 power. Again, the minus sign simply means a reciprocal. Reciprocate. Reciprocity. And so that's going to be 4. And then this is going to be 8. So if I plot those right here on a nice little picture frame. Oh, by the way, again, my base is a half. Well, what's half of 8? 4. What's half of 4? 2, and so forth and so on. So in actuality, I just need to do one of them and then just keep taking the halves. And then that'll give me all the points that I needed to graph this function. So the next point in sequence is going to be 1/16. And so I can graph my little function. 1, 2, 3. 1, 2, 3. Then I'll go 1, 2, 3, 4, 5, 6, 7, 8. Again, notice I'm not actually putting any points down here, because I know that my exponential function never gives me a negative answer. If I keep taking half of a positive number, I get a positive answer. So I'm not wasting my time doing all those extra points. So -3, 8 is right here. -2, 4 is right here. -1, 2, 0, 1, and then I go half, a quarter, an eighth. Next one will be a 16th, and so forth and so on. And so this graph right here will look like this, going down, 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 down. Basically, it kind of goes flat, but it actually is still going down. And so this right here is exponential decay. And with exponential decay right here, the graph is always getting smaller. This happens when your base is a proper fraction. A proper fraction is a fraction that's between 0 and 1. My favorite way to explain this is by using the cake story. Let's say your birthday comes up, right? And they give you a piece of cake. And of course, you being a mathematician, you say, you know what I'm going to do? I'm going to eat half of the cake that I have. So on the first day, you being greedy, you just slice off half that bad boy, and yum, 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 yum. And so half the cake's gone. You put it in the fridge, you know. The next day, you come by, and then you go, well, I'm going to eat half the cake I have. Well, first you ate one half right here. Then I'm going to cut that cake cut what I have in half and eat that half. Yum, yum, yum. So I'm going to eat a quarter. So that's right here, 1/2. That's 1/4. And so the next day, I said, well, I only got this little wedge right here. So I'm going to cut that in half. And I'm going to eat this piece right here. That's 1/8. Right. So my question to you, if I keep doing this, how long before I run out of cake? Right? Because I started with one whole cake. Then I have a half left. Then I had a quarter left. Then I had an eighth left. How long before I run out of cake? How long before I have 0 cake? And when you think about it, cut this in half again. 1/16. If you think about it for a while, you realize that I will never run out of cake. Because I'm always cutting what I have in half, saving a half and eating the other half. So of course that means I will never go hungry. Because I will always have something to eat. Yeah, right. Even on some days you can literally take 2 halves, cut a half and then say, I'm still hungry, cut another half off and eat that again. Right. And so what you have right here is you have less cake each time, but you never actually run out of cake. And so what happens is the amount of cake you will have will always hover above the 0. Because you never run out of cake. And so because of that, we call that asymptotic behavior. We're getting closer and closer to eating all the cake. We're getting closer and closer to eating all, but we never actually eat all the cake. If I look at this graph right here and I want to determine the properties, I will see that the domain still all real numbers. Negative infinity, the graph extends in both directions forever. But the range, again, will be from 0 to infinity. Even though this is now a decreasing graph instead of the increasing graph I had a while ago, the range is still 0 to infinity. Look at that. Still 0 to infinity. And then if I look at whether my y-intercept, our y-intercept is still 0, 1. The difference here is that this is a decreasing graph. And this is because my base is a fraction, 1/2. Last but not least, this graph has a horizontal asymptote of y equals 0. Thank you. We'll move on to the next section.